This question came in 2008 for 2 marks for EC gate. So the question states silicon is doped with boron. As soon as we say boron, it's an acceptor impurity, so we're doping it with Na to a concentration of 4 times 10 power 17 atoms per centimeter cube. Assuming the intrinsic carrier concentration of silicon to be 1.5 times 10 power 10 per centimeter cube, and the value of Kt by Q, Vt, which is also given 25 millivolts at room temperature, 300 Kelvin. Now the question that states here is, compared to undoped silicon, the Fermi energy level of doped silicon, what happens to it? Okay, they've given 4 options. So if you see this, they want us to compare what happens to a doped silicon with respect to undoped silicon in terms of Fermi energy level. So let's see, if we have an intrinsic silicon, let's say it is pure silicon, the energy band diagram would be like this: EC, EV, and there is this Fermi energy level for intrinsic semiconductor, which is EFI, is also called EI, intrinsic Fermi energy level. Now if we dope this with acceptor impurities, this becomes a p-type silicon, okay, where the hole concentration is far greater than electron concentration. Now the energy band diagram would look like this, where EI is for our reference, has always been throughout the course, and the Fermi energy level would be below EI. We have seen this because hole concentration is far greater than electron concentration. EF will be below EI and it will be close to EV. Whereas if it is n-type semiconductor, where electron concentration would have been higher compared to hole concentration, hence EF would have been on the upper half of this energy band gap. Now given it is p-type semiconductor, EF would be below EI. So if you compare this with respect to an undoped silicon for p-type, the EF goes down below EI, right, with respect to intrinsic semiconductor. So it will go down, so going up is not an option, so it's going to go down. Okay, so in order to find the exact value, either it is 0.13 electron volt or 0.427 electron volt, we have an expression which is giving EI minus EF difference, which is given by Kt ln of hole concentration over intrinsic carrier concentration. Okay, now we have all these values Kt, P and Ni. All we have to do is find this difference. Now if you put this, Kt is in electron volts. If Kt by Q is 25 millivolts, Kt would be 25 milli electron volts. So I'm going to write this here, 25 milli electron volts. And ln of the P is nothing but Na, because majority carrier concentration in p-type semiconductor. So this is 4 times 10 power 17 per centimeter cube. And Ni is 1.5 times 10 power 10 per centimeter cube. Now if I write this, ln of, now I'm going to write 4 over 1.5 times 10 power 7. So let me find this value. Okay, it becomes 2.66 times 10 power 7. Okay, now ln of answer, which is 25 milli electron volts times 17.09, which would be times 0.025, 0.427 electron volts. So we can see here the Fermi energy level of doped silicon compared to an undoped silicon would go down by 0.427 electron volts. So we are seeing here intrinsic semiconductor which is undoped. Compared to this, for p-type semiconductor, the Fermi energy level would go down here with respect to this concentration by 0.427 electron volts.